Okay, so in the last class we talked about how maybe the more covalent salt, lithium chloride, was more soluble in organic solvents because it's nonpolar. So that's based off of the very kind of primitive notion that like dissolves like. So that's fine. But I mentioned that water solubility is a little bit different. And so I'll kind of illustrate why. So when we talk about solubility, what we're doing is we're trying to break intermolecular interactions. So when you form an extended solid, you have molecules interacting with each other. We want to break those interactions up and have them as dissolved individual species within the solution. So imagine that if I have my, let's say, sodium chloride, I have this extended lattice. Here's my sodium chloride ions, not drawing 3D structures, but they pack. And then so here we're forming our salt crystal. Here's my little box crystal. Okay, that's a crystal. So this is in a solid form. And then so when we try to dissolve it in water, so we add our water plus H2O, we have water molecules coming in. And like we mentioned in last class, we have our dipole moment within water due to the high polarizing ability of the proton. So we have delta minus, delta plus. And then so when we have our cations in the salt, our delta minus will go here. We have our water this way. We can have our delta plus associated with the anion this way. And then, so ultimately, when we dissolve it, we then form solvated ions. So for an ion to be solvated, it has solvent molecules, in this case water, associated with it. So if we have our chloride, then again, it's going to have interactions with our delta positive of our water. So you have like this guy. And then we can fit maybe a number of them around it. I'm not drawing actual geometry, but there are published examples of what a chloride would look like. We have multiple ones. And then so our delta positive here could stabilize a negative charge. So I'll just draw one more. OK, so far so good. And then we have our sodium ion doing the same thing. So I'll draw it over here. Here's sodium. Oops, I'll do sodium in green. Sodium plus. And again, we have waters nearby. This time, our delta minus charge is going to be around. OK, I'm only going to draw a couple of these. Oops, like so. But there's a bunch of them around, which we'll talk about how many there are a little bit later. OK, so let's see. Yes, so this is our overall solubility. So when we talk about like the reaction of something being soluble, here's our general equation. So in this case, sodium chloride as a solid, right, is going to plus water. And then when it dissolves, it's in equilibrium because we can saturate it, and then it'll be dynamic equilibrium between a solid and the solution. Then we have aqueous sodium plus and aqueous chloride. And then when we talk about these aqueous species, these are the solvated ions is what we're talking about. So we want to think about this, like what makes something soluble. We have every salt that dissolves is going to have some sort of equilibrium constant. So that's what we call KSP. Right? And that's going to be equal to the equilibrium constant of this reaction, which will be over, and in this case, because these are liquid and solid, we kind of have the whole idea of one, right? Because they have that activity. So far so good. So because we can put numbers on this, on solubility, that means that we can think about this in terms of thermodynamics. So if you remember back to Gen Chem, we were talking about free energy. And then so the free energy of a reaction, delta G, equals negative RT, so the gas constant times the temperature, times the natural log of K, of an equilibrium reaction. So if we're talking about the free energy of solubility, so I'll call this of solubility, the free energy of just like something dissolving is going to be related to that equilibrium constant of dissolving. So And then this means that we can also think about this in terms of enthalpy and entropy. So again, this is our enthalpy of dissolving something, of solubility, or yes. And then delta H minus T delta S of the same process. OK. So the reason I want to talk about that is because now we can think about these in terms of numbers, and then we can, if we have numbers on these, we can maybe compare what makes something more soluble than something else. So I do want to talk about that. So let's see. Yes. For this kind of discussion, we're going to ignore the entropy component. Of course, it matters because one aspect is that as you go from a salt to a solution, we're increasing entropy. So that's always increasing. But I want to talk about other energetic factors that go into what makes something soluble. So we'll focus on the enthalpy component for now. OK, so if we want to think about the enthalpy of dissolving something in water, we can make a thermochemical cycle. So we had that one reaction, which was the salt going to the aqueous ions. But we can think about it in terms of 3 different things. So let me rewrite that equation here. So the dissolving component that we were talking about was if we had some sort of mx salt. So in that case, we just did sodium chloride as a solid. And we were trying to find, sorry, it's running out of ink. We're trying to find what happens when you go to, I'll call these monocationic, monoanionic for now. But of course, these could be dicationic, et cetera, et cetera. OK, so we wanted to find the energy of this, or the enthalpy of this. So we wanted to know delta H of dissolving. And so we don't know this. And then we want to find out what factors that's related to. So we could, in principle, break this down into 2 steps. So thermodynamics is path independent, right? We should be able to go any path as long as we get from the starting point to the ending point. And then our free energy and our enthalpies should add up to the same idea. So what we could do is we could think about going, let's say, down here. So our solid state salt, what happens if we go to the gas phase ions, so not solvated. So we have some sort of delta H here. And then we can go from this, the gas phase ions, and then we just need to solvate them. So in this case, this will be, add H2O, and then we have a delta H2. And so what we're saying is we're going down, taking 2 steps to get to this final product. And then this delta H should be equal to the sum of both of these, because we're going from the same starting point, same ending point. And then so it turns out that these 2 components actually have names. So this delta H from going from the solid state salt to the gas phase ions is called the lattice energy. So you might have seen that before. So it's, yes, the lattice energy is just how stable your salt is typically. And then this going from the gas phase ions and then adding water to it is called the enthalpy of hydration. So enthalpy, let me label this. Hydration. And then this is called the lattice enthalpy. And so the enthalpy of hydration is because this gas phase ion doesn't have waters bound yet, but we said before that the aqueous ions have that solvation shell. So there's a number of waters bound to it. And so, of course, this forming bonds releases energy is exothermic. So the enthalpy of hydration is going to be exothermic. It's less than 0. Here, we're going from a solid state to the gas phase, so that's always endothermic. We're breaking bonds, you have to put energy in to do that. So delta H lattice energy is always greater than 0. So therefore, the kind of major takeaway is that the delta H of dissolving something, or enthalpy of dissolving something, is going to be equal to delta H lattice plus delta H hydration. Oops, that's an H. And then so as a result, this could be positive or negative. So yes, it depends on how these two compare. If your enthalpy of hydration is very, very negative, you're going to be releasing energy when you dissolve something. If it's not as negative as the last enthalpy, then you're going to be, it'll take energy or take heat to dissolve something. And then there are actually some examples. So for example, if we dissolve lithium chloride, it's exothermic. So your solution will get hotter as you dissolve it. If we had something like ammonium nitrate, it's endothermic. And it'll actually get colder as you dissolve it. But it'll still dissolve because entropy drives that overall free energy. But you will feel it get cold. So that's pretty cool. If you want some sort of energetic diagram, I kind of have one. So let's see. I like the green. So what we have is we have our solid. So this is my little salt crystal. And then what we're doing is we're then going to the gas phase. So this is our gas phase ions. And then so this energy difference to go from the solid state to the gas phase is our delta H lattice enthalpy. And then finally, I'm going to arbitrarily draw it as having the solvated ions below. So this will be an exothermic reaction. But of course, like I just said, it could be endothermic. These are our solvated ions. And then so this would be going down. Here is our delta H of hydration. And then this difference, so between these two, this will be our enthalpy of dissolving something. OK, fantastic. So these are the two same pictures, but some people find one easier to look at than the other. OK, let's see. I had some comments. What governs the enthalpies? So first, we'll talk about lattice enthalpy. So here's our lattice enthalpy. So basically, the more ionic it is, then your delta H lattice will go up. That makes sense, kind of what we've been talking about, right? By having the difference electronegativity very high, we can have separate localized charges, and then it stabilizes the 3D lattice more compared to a more covalent thing where your intermolecular interactions are weaker. OK, although I will say size also matters. Also matters. And that has to do with the charge density of what you have. OK. How am I on time? OK. So I'm going to quickly erase, and then we'll talk about what governs the enthalpy of hydration in the next video.